Okay, let's take a look at the data that we'll be using as an example for this logistic regression. Okay, so we're going again to look at the height and weight data from before, but we're also going to include sex now. So you can read these data into R. There's a new file, it's called htwt2.csv. And so you can just read that into R. And we can take a look and just see how height and weight differ depending on the sex in this data set. So here we're just doing that with ggplot, and we're looking at the differences in height between females and males. And so we can see, not surprisingly, we see differences. We can also take a look at differences in weight, and we see differences as well, but perhaps less difference in weight than we saw in height. So first we need to organize the data, just like we always need to do. So sex is, we need to make that a factor. So here we're creating, or just converting that to a factor. And then the sex will be the number version of that factor. So when we first do this, being female will be 1 and male will be 2. So remember, this is alphabetical. So R is just going to assign numbers to each levels in our categorical variables alphabetically. So that's going to make females 1 and males 2. But for logistic regression, one value has to be 0 and the other has to be 1. So we can just subtract 1 from the original values, and that's going to make females 0 and males 1. And so that's going to be our sex variable, our predicted variable, where everyone is going to be either a 0 or a 1, depending on if they're female or male. And then we're just getting our sample size here. So capital N is just going to be the length of that sex vector. Then we need to organize the height and weight data. So here we're just standardizing. So both of these are metric. So we're standardizing them the way that we have throughout the course. So nothing new here. And then, so normally we could just then make our data list and run the model and get into how to do that. But what I'm going to show you now here is to how to use the generated quantities block in Stan to do the posterior predictive check. And again, you don't have to do this, but it's actually easier to do it in Stan than it is to do it in R, like to do all the calculations yourself in R. But what we need to do, if we don't want to do the posterior predictive checks on every individual in our data set or every record in our data set, which will end up making a huge matrix at the end, we need to specify the data that we want to do the posterior predictive checks for. We need to do that ahead of time and send that information to Stan at the same time as we send all of our other data. So here I'm doing that. So this is the same sort of things that we've done before with posterior predictive checks. It's just now we're doing it before we've actually run the model. So here I'm just setting the number for how many data points we want to use for the posterior predictive check. So I'm just going to take 20. So I'm going to call that pred check n. So the sample size for our posterior predictive checks is going to be 20. And then what I want to select these 20 individuals from throughout our data set. And so what we've done in the past is done this with a sequence from 1 to our sample size with the length of how many individuals that we want to sample. And if you remember, when we've done this in the past, this is not going to give us integers. It's going to give us floating point numbers with decimal points. And that's not what we want. We want kind of an indicator of which individuals we're sampling. So we want it to be an integer. So I've rounded those numbers, and that will give us integers. So our predicted individuals, the individuals that we're going to use for our predictive check, are going to be drawn from throughout our original. It's going to randomly draw, not randomly, it's going evenly spaced 20 individuals from throughout the data set. And then here I'm just getting the height of these particular individuals, the weight of these particular individuals, and the sex of these particular individuals. And I'm calling them pred height for the heights that we're using for our predictive checks, the weights, pred weight for the weights we're using for our predictive checks, and pred sex for the sex of our individuals that we're using for our posterior predictive checks. So none of this should be new to you, but doing it right now is what's new. So now we have all of our data ready to send to stand. So most of this is what we've done before. So we have our sample size, our sex variable, our height, our standardized height data, and our standardized weight data. So that's really for building the model. And then these last three are for our posterior predictive checks. So we have our sample size for our posterior predictive checks, and then the height and the weight data for those individuals that we want to run this check on. So this is a little bit different than what we've done before, but it's not too different. Then we can define the model. Okay, so we're going to start with our data block. So this is the same as what we just did for our data list. So we're setting our sample size is n. We have our sex variable, which is an integer, right? So although it is a vector, we have to tell Stan that it's integers, so that's indicating a 0 or a 1, and it's not an actual value. So that's of size n. And then we have vectors of our height and weight data. We also have just an integer value for the sample size of our posterior predictive checks, and then vectors for the height and weight data that we're using for our posterior predictive checks. And so remember, these are different size. Like all of these vectors are our original sample size, but we're doing a smaller sample size for the posterior predictive check. And so we have to indicate that different size here and make sure that we've told Stan that we've defined that sample size in Stan as well. Okay, the parameters block, nothing's new here, right? We have our intercept, our effective height on the probability of sex, and our effective weight on the probability of sex. So it's really the probability of male. Whatever is 1, it's the probability of that. Okay, then we can move on to our model block. And so again, this isn't going to look very different from what we've done before, right? So for our likelihood, we're going through each sample, and the mean for that, it's just the sum of all of our predictor variables. So here we have metric predictor variables, but we could also have included categorical variables or a mixture of metric and categorical variables. We just include them here in our calculation of mu the way we would before. And then what's different is now instead of a normal distribution, we're using this Bernoulli-Logit function, where again, so mu of I, it's really the probability of this individual being male, being 1. And that's coming from a Bernoulli-Logit function. And then we have our priors set up just the same way that we did before. So having our model set up in this way doesn't change anything in terms of our priors. So not too different from what we've already learned to make it a logistic regression. Okay, so normally our model would be done here, but now what we can do is add this generated quantities block. And so this will do our posterior predictive checks for us. And so what you can see here is I'm going to kind of walk through it backwards. And so it's going to look almost exactly the same as our likelihood, except for now our sample size is different. So now for I and 1 to the sample size for our predictive check instead of 1 through n. And then we have our predictor variables and their relationships, except for now instead of our original z height and z weight, we're using just the individuals that we're predicting the height and weight from. But other than that, these are the same. And these are going into the mean predicted variable. And then our actual predicted variables, again, are coming, but now we have an equal sign because we're not estimating it from a distribution. We're actually getting a random draws from the Bernoulli-Logit function. And so all the function in Stan also have this underscore RNG, which is a random number generator from that distribution. And so here we're calculating the predicted, if an individual is male or female, by randomly drawing from the Bernoulli-Logit distribution with a mean of the mu underscore pred I here, which is what we defined up here. So this is almost the same as our likelihood, right? Our likelihood was mu sub I is all of these, and then the sec sub I is from a Bernoulli-Logit here. The difference now is that we're calling it mu pred is just the sum of those, making sure that we're just using the weight and height for the individuals that we want to do the posterior predictive check on, and then using that mean with our Bernoulli-Logit random number generator to generate whether or not individuals are males or females. So again, it's very similar to the likelihood, but instead we have to define any variables before we actually use them in an equation. So mu underscore pred and y underscore pred we haven't defined yet, so that's why we have to define them here, and the same way that we would define them in the data block. And so mu underscore pred is going to be a vector of the length of our posterior predictive check, and similar with y underscore pred. So we're defining the variables that we're going to use, and then we make a loop just like the likelihood. Here, the only difference is kind of which individuals we're using, and then instead of using the tilde here, we're using equals, and we're using the Bernoulli-Logit random number generator. And so what this is going to do is we could store the mu pred or the y pred. We're just going to store the y pred for this, and it's going to include that in our output. So let's see what that would look like. So then we can run the model. And so here we're just going to keep beta 0, beta 1, beta 2, and the y underscore pred values. Then we can run stan and look at it. And so now you can see we have our estimates for each of these, but then we also have our estimates for each of the 20 individuals that we included for the posterior predictive check. And again, there's going to be a record for these for each step in the chain. But so we can see that all of our r hat values are 1, so everything is looking good. When we look at our effects, so here we have our intercept. Beta 1 was the effect of height on whether or not an individual is male or female, and so we can see that height had a pretty strong effect. Weight had a positive effect as well, but it wasn't as strong as height, and that makes sense, right? When we looked at the data before, we saw bigger differences in heights between males and females than we did in weights. And so the posterior distributions for our coefficients here fit. That makes sense. So then we can extract the data. This isn't any different than what we've done before. So we can extract them as a data frame and then parse out the values for each of our coefficients. We can convert those to the original scale if we want to. So here I've done that. This isn't anything new. We've done this before. And then we can plot the posterior distributions. So I'm not going through the code here because we've done this a lot now, and you have the code in the R file for this. So we can see the mean effect of height on whether or not an individual is male or female is 0.59 with a 95% highest density interval of 0.4 to 0.82. And you can see similar data for the weight here. So one question is, what does this actually mean? So what is the effect of 0.59 of height on an individual's weight mean, or sorry, on an individual's sex mean in a logistic regression? So now remember, it's not just a linear combination of our predictors that gives us our predicted variable. We've put it through the logistic transformation. And so the meaning of these coefficients is a little bit different than what they were before. So the coefficients of a logistic regression tell us about the log odds. So it's the log of probability being 1 versus the probability of being 0. So a way of interpreting this then is that when x1 increases by 1 unit, the log odds of the predicted variable being 1 increases by beta I units, so whatever your predictor variable is. So for our particular data, this is saying that when height increases by 1 inch, the log odds of being a male increases by about 0.592, or by about 0.59. So that's the interpretation of coefficients in a logistic regression. Okay, so now we can look at our posterior predictive checks. So I'm not going to go through the code here because it's the same as what we did before, where we separate out the y_pred values and then summarize them, get the mean and the lower and upper highest density interval values, and then we can plot them. And so here I plotted our predicted values. Our predicted individuals, and I just put a dash line here for 0.5. So individuals on this side our model thinks are males, and individuals on this side our model thinks are females. And so the red dots are the actual sex of each of these individuals. And so you can see our model did pretty well. Like, most of the individuals that it thought were males, and most of the individuals that thought were females were females. But there are some differences, right? So these represent individuals that our model thought were males, but were actually females. Then there's some on the other side too. So these represent individuals that our model thought were males, or were females, but are actually males. But that's okay. We expect our model to not get everything just right. Okay, so that's essentially it for logistic regression, and then using the generated quantities block of Stan. Hopefully that makes sense. You can work through the code in the file that I sent, and yeah, that should be it. So now we'll move on to count-based predicted variables.